Hola! Hola! Hola, Alicante! So, as you can see, I'm so excited to be here. And first of all, I just want to thank the organizers and the sponsors of React Alicante. Yeah. And of course, I want to thank all of you for being here and for my talk. So this is Seek and you shall find your way to fun. So we shall see. So first, a question for you all. Does anybody here have a side project, a pet project that you're passionate about? Anybody? OK, lots of you. Anybody ever finished the project? OK. Oh, there are some finishers. That's awesome. Well, I also have a side project. And like Dan, I actually don't always finish them. But I have a side project, and I'd love to share that with you today. So who am I? So my name is Kevin MAES, and I'm a developer from the United States. I've spent the last couple of decades between New York City and Philadelphia. But I'm super excited because a couple months ago, my family and I, we actually moved here to Spain, and we live in Malaga. So that's awesome. In fact, have you all seen this photo by now, this viral photo? It's like really amazing what AI, photo image generation, can do these days. It's incredible. So I work as an engineer at a company called Stately, where I build software for people like you to help you to collaborate and to model flows using diagrams and state machines. OK. So first, let's get something out of the way in terms of terminology, right? So in Belgium, this is a beer, OK? And it's pronounced MAES. But in English, we say maize. OK, now this is corn. In fact, it's a corn maze. And in Spanish, this is maíz. But in English, we say maize. And this, you know what this is? This is just a maze, OK? So this is a lightning talk, so we don't have any more time for puns. So I just wanted to get that out of the way. All right. So why mazes? Well, a few years ago, I started playing around with mazes, specifically maze generation. And I came to realize that this topic is built upon this huge foundation of interesting concepts. And some of them I actually work with on a daily basis. So today, I want to take you with me down the path towards discovering mazes. So vámonos, let's go. Now, our starting point is just a little bit of graph theory, OK? So graph theory is the study of entities and relationships between them represented by connected paths. Graphs are like networks, and they're made up of nodes. Now, these nodes are connected by edges. And you know that graphs do affect us as engineers every day, right? We have dependencies in our node modules. We have just navigation, web navigation in general. There's the React component tree, for example. And then, of course, there's state management and data flow. Now, graph theory can also help us chart the most direct or the fastest way to travel between points, for example, on a map. You see what I did there? Now, as I said, I live in Malaga, but in order to fly to Alicante, I actually had to fly through Madrid. I could have driven, actually, but then I wouldn't have worked on these slides during the plane. But what I really wanted to do, of course, is to take a direct flight to the conference right here. But at least there was no jet lag. So now on to mazes. Maze generation involves creating and navigating a network of interconnected paths. And that basically sounds like a graph. So if you consider the start and end of a maze and all of the steps it takes to travel between those 2 points. Now, we can use graph traversal techniques to both create and solve mazes. So today, though, we're going to talk about maze generation. So the technique that we need is depth-first search, or DFS. And what that is basically starting at a certain node and diving in as deeply as possible into the graph until you can't get any further, and then backtracking back up to explore new paths. Yeah, that transition is kind of awkward, sorry. For the purposes of creating mazes, though, it can be helpful for us to arrange our graph into more of a grid. So we can convert graph nodes into grid cells. And the grid has its own columns and rows. Columns and rows are given index numbers, like 0 and 1, 2, etc. Now, one key change is that the grid lines separating each cell, now they don't represent the edges connecting our graph nodes, right? In fact, these lines represent the absence of edges between nodes, as the cell walls basically block those connections, at least for now. So grid cells each have their own index number, flowing left to right, top row down to the bottom. And we've converted our graph to a grid. Now, most regular-looking mazes with shapes like squares, rectangles, triangles, even hexagons, these are all built on top of some grid system. However, there are some mazes that are irregular, maybe natural-looking, organic-looking, and they don't need to conform to a grid system. But they can still be said to function as a graph. Now, one common way to code a grid is by creating a 2D array. That's an array where elements might represent the rows of the grid, and each element contains its own array of the column cells for that row. But I think it's actually easier to just flatten this out into a single array of cells. However, it's going to be crucial for us to be able to access any cell we want very quickly. So how do we do this? Well, we know that the index numbers flow left to right, top to bottom. And of course, we also know the total number of columns, in this case, is 3. So we can just use math. So for example, to get a cell's row index or its column index, all you need is its index and its number of columns. Likewise, to get any cell's index number, if you have its row index and its column index, and of course you know the number of columns, you can get that too. So the cool thing is that now if your grid is really large and you have a huge array, there's no more need for nested arrays or O of n array iteration. So if you want to work with grids, you can take a photo of the slide, or you can just send it out later, but I think this is pretty handy, and I use this too. So we all use algorithms to some extent in our work, right? And algorithms are often implemented with functions, loops, and recursion. Now, state is temporarily stored almost implicitly in variable values. Now, at Stately, we use state charts. And these are like flows built upon state machines. They also happen to be representations of directed graphs, which are basically graphs that have paths with specified direction. Now, you can model software and export to JavaScript and TypeScript code to XState, which is a state orchestration library from Stately Studio. And it can sometimes, for me, be helpful to see algorithms as state charts for a few reasons. First of all, you can get a visual understanding of how the algorithm works, and that's always nice. You can also see a breakdown of the discrete steps that make up the algorithm. So an example might be looking at the base case compared to the recursive case. And you can also, using state charts with a library like XState, you can actually spread out the implementation of an algorithm over time in your software program. So let's dive deeper into an example from our MAES generation. But first I'm going to get water. Can I get that water bottle right there? Sorry. Oh. OK, sorry about that. So the most basic pathfinding algorithm for MAES generation is the recursive backtracker. And then this is a version of DFS, or that depth first search. So in this state chart, we have states like idle and seeking, advancing, backtracking, finished. And we also have certain events that transition us between those states, like start, or always, or after, and that just waits a certain amount of time. You can see here conditions to check whether we're in a dead end or back at the start. That's part of the backtracking. So how the algorithm works is this. Within our grid of cells, we begin in a starting cell. From there, we're going to move to the seeking state in order to seek out a path. So we need to represent that path using a stack or a LIFO, last in, first out array. And in the seeking state, we need to basically search around in all 4 directions, the top, the right, the bottom, and the left. And what we're looking for is a neighbor that we've not yet visited before. So then, once we find a neighbor, then we go to the advancing state, and we visit this neighbor by marking it as having been visited. So we add that cell to our path by pushing it onto the stack, and then we remove the walls between those 2 cells. Now, this algorithm is recursive because, of course, we have to keep on repeating this over and over until we hit a dead end. And then it has backtracking, because we need to backtrack to the last cell that still had unvisited neighbors. And backtracking will cause us to pop off cells from the stack and continue in a new direction if we can. So eventually, all the cells will have been visited, and we'll be back at the start. And at that point, we're finished. Now, the example I just showed uses P5.js. And P5 is a library for creating interactive graphics and animations for the browser. It's inspired by something called processing, which is a language used for generative art. Now, all of the initial MAES prototypes I created were done with P5. But another option we have for the web, as we saw earlier, is HTML5 Canvas. So for my project, I combined React, Canvas, and state charts using XState to create a new version of a MAES generator. Should we take a look? Okay. All right, let's see. Displays and mirror. Okay. Okay, there it is. Great. Now let's see the sound. Da-da. Okay. Okay, welcome to the MAES generator. And you can see we have the grid that we talked about. And I've already punched out like an opening at the beginning cell and then at the end so that we could actually solve this maze. And I'm just going to go over here and play. So just like in the P5 examples, you can see that the recursive backtracker sort of takes on a life of its own. It seeks out new paths, it hits dead ends, and then it backtracks, and so on and so forth until the entire maze has been drawn. So if we look at that again, we can also hit a pause button. We could step forward one cell at a time. We could hit the resume. And what that means is that we have complete control over this algorithm at runtime via the state machine. We can send events to the state machine, and the machine knows how and when to handle those events. In fact, we can even use, let's say, spacebar to start it off, pause, right arrow, hold down the right arrow, pause again, and that means that we can send those same events to the state machine via user gestures from the mouse or from the keyboard or what have you. Okay, so let's bump this up to 65 frames per second, let's say, and make this grid a little bit larger. All right, here we go. Okay, so now you see that things are going faster. It's a little bit mesmerizing. And it's also very smooth performance. I don't know if you noticed. So we're using React for the UI here, but React is holding onto a ref, which basically gives access to the Canvas 2D tag and all of its Canvas API. So for example, Canvas has a draw method, and believe it or not, the entire maze is being redrawn with every single frame there. So it's very fast, and it looks pretty good. Now, I don't know, does anyone want to see it like at 200 frames per second? Okay. Okay, don't blink. All right, so this is like really smooth animation, so that's really cool. All right, let's see here. Oh, and one other thing is that if you convert the frames per second to milliseconds, then XState is actually able to delay sending the events to the machine, so you effectively have control over the speed of the animation, in this program. All right, so let's see, refresh here. Okay, now listen, I know you guys didn't request this, but I took the liberty to go ahead and add gratuitous sounds to this application. Okay? I'm an ex-Flash person, that's what we do. So, let me just set this up here. So I'm going to turn on this sound. Maybe I'm going to change this a little lower. And it might be a little loud, so I'm going to maybe put it here, and we'll see how it goes. All right, ready? Oops. Okay, so you can see that the sound is actually in sync with the motion and directionality of the head, or whatever this is, the current cell, let's call it. And this is just a scale. This is a diatonic scale, happens to be key of C. But you can make it sadder and minor if you want. You can make it chromatic, whatever you want. Okay, now, oh, you like that? Okay, so check this out. What about an arpeggio? That sounds like fun. kind of sounds like an 80s arcade game, sort of. Okay, now, in this case, I had to take a few liberties with the pitch because even though we have 8 octaves of notes, we can actually run out of pitches, so I sort of have to cycle back over, you know, or pick something random or whatever I did here. So there you go. Okay, cool. Oh, thank you. Now, this application is using a use sound hook, which by Josh Camo, which is an abstraction over something called Howler.js. Has anyone actually used either of those things, like Howler.js? Cool. All right. All right. Does anyone want to see this at 200 frames a second? Okay, here we go. Ah, okay, we're done. Well, okay, so that was crazy. So there you have it. I mean, that's fun with maze generation and you know, with sounds and things like that. So that's pretty much what I wanted to show you, and you know, for now. So let's get out of this. Hold on. Why is this not letting me out of here? Okay. Stop mirroring. Just play. Okay, so here's the state machine for the overall application. Now, all of this is mostly for the UI and the UI controls. So, for example, moving the levers for the frames per second and the number of rows and columns, that just sends events to the machine, as we talked about. Now, in the middle here, we can also see a big generating state, which invokes a recursive backtracker machine, and that's the one we saw earlier. So there are many other algorithms for generating mazes, but these can vary by visual style, difficulty in solving, and algorithmic complexity. So keeping all these machines separate actually allows us to potentially swap out the recursive backtracker algorithm for a different algorithm. I just need more time in the day. Now, all of these state charts were created at Stately Studio, and you can just visit state.new to try them out for yourself in your applications. Okay, now I know the question that you've all been waiting for is, what about mazes and AI, right? So one thing's for sure, AI image generation, as we saw earlier, I mean, it's amazing. And DALL-E and all those, Dream Studio, Midjourney, they can create some really impressive, beautiful, convincing-looking mazes. But they can't really ensure that those mazes are actually solvable. And these aren't really solvable, right? Or at least not based solely on the visual training data that they rely on. So there are a couple of workarounds potentially. One is purpose-built models, where they can generate mazes based on maze generation algorithms, like we did. There's also post-generation validation, where after they've generated a maze, they can actually run a maze-solving algorithm to see whether it's valid. So the good news here, though, is that if your full-time job is creating solvable mazes, I don't foresee AI taking your job anytime soon. Okay? Wait, what? What the heck? What? Oh, bad news, guys. It turns out that ChatGPT-4 can actually create for you code for a maze generation algorithm with React, Canvas, XState, and TypeScript. Now, I haven't dropped this into our code sandbox to see if it actually works, but why don't you all give it a try and let me know? But seriously, if you actually think any of this is cool, come and see me. I'd love to talk to you about it. So what can we do to beat the AI? Well, we can focus on the human qualities that we've enjoyed since childhood, like our innate curiosity and our drive for discovery and our creativity and sense of adventure. And while we're at it, maybe even add a splash of color to your work or bring back some sounds to the web. In a world of structure and rules, I love mazes because they allow me to wander and to explore and to even get a little bit lost. So I really encourage you to seek out your own passions and to get lost in your side projects. If you're anything like me, you may never see them to the end, but you'll be so grateful for the fun they bring you every step of the way.